Hi there, Dr. Fox here again on the series of lessons for the AQA A-Level Physics, Astrophysics unit. This is lesson 13, the last lesson, in fact. Unlucky for some, but lucky for you, it's the last time you have to listen to my voice. We're doing astrophysics anyway. This one is basically cosmology. It's Hubble's law and quasars. In other words, we're talking about the big stuff, the Big Bang, the Hubble law, the age of the universe, and quasars, these objects right at the very early phase of the universe. They're very distant, but of course when we go distant, we go early. We're going to talk about the evidence of the Big Bang, which is irrefutable. Please don't listen to lots of other videos saying about, well, it's just a theory, and if people do say that, they don't know what a theory is. Go and look at what a theory is first, that kind of thing. And absolutely fascinating, the piece of physics that have gone on, the measuring that's gone on with multiple different satellites, ground-based telescopes to be able to work this out. And a little bit about quasars. Quasars have their own little bit in the specification here, as you can see. But basically, this last bit is the big stuff. This is not the order in which it appears in the specification, by the way, but I'm going to do it this way. I've already mentioned about Redshift and its derivation of how you get this V here. It's written in the specification by odd. It just says Redshift V equals HD. So Redshift is how you work out the V in the V equals HD, and D is the distance. I'm going to show you the graph again. I've already mentioned about this law when we did about supernova, type 1a supernovae, but I'm going to do it again here. Because in this case, you have to estimate the age of the universe from h, which is the Hubble constant, which is given to you in the data sheet on the in the exam. And then it says simple interpretation as expansion of the universe. So in other words, the idea that because we see recessional velocities of galaxies, the universe must be expanding. But we also get a bit of detail into the other evidence, which we haven't talked about at GCSE, if you happen to do the triple award GCSE, in the English GCSE. And also something that's never been talked about, which is relevant abundance of hydrogen and helium, which really is the most amazing piece of science. Right, let's crack on. So again, look at what we've done. This is really good. This is all, effectively, nearly all, plus a little bit of the astrophysics unit. Pick 3, 4, 5 of these. Go away, write down what you know, check your notes. You have to keep doing this, otherwise you are just sitting there staring at YouTube videos. You need to learn this, and the only way to learn it is get a piece of paper and a pen and writing it out multiple times. There is no shortcut at all. So stop the video, do 3 of these first before you do anything else, just to get yourself back up to speed again with where we are. If there's been a gap between that, especially stuff on binary stars and exoplanets, that's quite hard. Okay, right, and you're back with me. So what is the evidence of the Big Bang? So we've got 3 aspects which you need to know for the A-level. Cosmic microwave background, which you've probably heard of from GCSE. You've got redshift of galaxies, which I've already mentioned, the idea that galaxies have a greater redshift the further away they are. And of course, we had some idea of how we measure the distances to the galaxies by using type 1a supernovae, but also I mentioned about the other methods as well. And then, of course, we've never mentioned this before, but the abundance of hydrogen and helium in the universe needs explaining. And it's very difficult to explain in other ways, apart from having a hot, dense period, which is what the technical way of referring to the Big Bang is. The Big Bang was actually a term of a bit of a mick take, saying, was there a Big Bang? But actually, it's a hot, dense period of the universe. And we're going to show the evidence that shows that that's explained. So the cosmic microwave background radiation is basically the afterglow of the Big Bang. It's about 14 billion years ago. It's 13.8-ish is the current good estimate, plus or minus about 40 million years. So we're getting there, but it is roughly those there. Now this is a picture of the microwave radiation, which is radiation that's coming from all over the sky. Doesn't matter where you point, you're getting a very small amount of heat, 2.71 Kelvin. I know it's not warm, but nevertheless it's still there, and that is the afterglow. That was actually predicted and then was found way back in the early part of the 20th century, and was found to, if there was a Big Bang, there had to be some energy left over, and there it is. And what was really interesting is these, they're called anisotropies, these ideas of slightly warmer and slightly cooler than 2.71, and this, we think, is the start of the formation of different areas of density of the universe, which gives the structure, the seemingly random structure we see today. So this picture was done by Kobe. There's been better ones done by WMAP, and there's quite a few other, Planck as well, these projects that have been up. But basically, cosmic microwave background Needs explaining. There is warmth coming from everywhere. That means there must have been a hot phase of the universe. Pigeons were initially to blame because these two chaps here, Quasars and Wilson, had this telescope, and it doesn't look like a telescope, but that's how you detect microwave. That's how you did detect microwave emission from the sky in the last century. And they kept thinking it was bacterial action from pigeons, and they kept scraping them out. Unbeknownst to them, somebody else was detecting it on the other side of the world, and they put things together and realised that they detected the afterglow of the Big Bang, and that's why they're looking so pleased. Why is it microwave? Well, it was very hot. It was a very hot period, and it was actually redshifted from the infrared. And the redshift was about 1,000. And so what actually happened is that 3000 K was about the temperature at which the universe started becoming transparent. And it's redshifted all the way to 3K. So what we'd expect to see. So in other words, we see a highly redshifted lump of heat effectively coming from everywhere in the sky in the microwave band, and it's been redshifted from the infrared. So redshift, of course, longer wavelengths. Infrared to microwave is going from longer wavelength. Your fact file for the CMB, perfect black body. Remember we talked about black body with Wien's law, the idea of temperature and a wavelength are related to each other, inversely related to them. It's coming from everywhere, and also it's the heat of the Big Bang, the afterglow. So that's why we know there was a hot phase. The next one, of course, is the fact that wherever we look, galaxies are receding. And the further we look, the faster they're moving away. And of course, we now know they're accelerating. However, this is the non-accelerating part of the graph. In other words, this distance isn't greater. When Hubble did it, he couldn't go very faint, therefore he couldn't go very far, and therefore there is a linear relationship between these at lower distances, which comes up with this number of 65 kilometers per second per megaparsec. Don't say that with a mouthful of crisps. It's odd because it's 65 kilometers per second, which gives a reasonable number per megaparsec. Megaparsecs, of course, are used because that's the distances of the nearest, furthest stars, if you see what I mean. The galaxies are. The galaxies are a long way off, but not so far away that you start seeing the acceleration. So from this graph, the inverse of the gradient, which is the Hubble constant, is the age of the universe. Now, the difficulty with getting an inverse, you think, 1/65, I can do that. No. You've got to get rid of kilometers per second, so therefore what I would do is convert it into thousands. Then you've got to get rid of the mega. So if it's 65,000 meters per second per megaparsec, how many is it per parsec? So you can see it's a lot less than that, because you would have that per parsec, so therefore you'd have a lot less than that. And then, of course, then you have to invert it, convert it all to meters, and then you end up with a number that's around the 15 billion that we talked about, 14, 15 billion that we had before in years, and you have to change that to years, of course, from that. So there's quite a bit. I would do that now. I would go away and invert that and make sure you're getting the right number. You're getting basically billions of years. Usually 10 to the 10, something like that is what you'd expect in years, and you have to convert. The only hard bit about getting the edge of the universe for Hubble constant is units, and that's it. Converting is quite straightforward, but when you've got kilometers, how many's in there, how many's in a parsec, you end up getting very confused. My top tip of conversion is there going to be more of them, or is there going to be less of them? So how do I convert from meters to millimeters? I've got 1 meter. Is there more millimeters in a meter than there's more of them, right? So you multiply by 1,000 because that's how many millimeters in a meter. If I'm trying to work out how many meters in a centimeter, is there less? Yes, there is. So therefore, my number is going to be lower. So I divide by a number. So just think of it like that. I still think of it now, even though I've been teaching physics for 20 years. Okay. The last one is brand new to most of you, which is the hydrogen-helium abundance. Now, there's a lot going on this slide, so bear with me on this one. Basically, at the start of the universe, all you had was a soup of fundamental particles, protons, neutrons, probably, and they were smashing together. You had a proton on its own, of course, is hydrogen. Neutron on its own is a neutron. And you were smashing together. You were producing lots of different things like deuterium and tritium, and they all came together and produced helium. Now, there was only a very short period of time where that could have happened. In other words, when the universe was dense enough to cause fusion, dense and hot enough. Hot, because you need the heat to be able to give it the energy to be able to smack them together. Dense, and they're all in the same place, therefore it's more likely to happen. So therefore, you've got a very, very small period of time where hydrogen, protons and neutrons can make deuterium, and then deuterium and tritium, which are isotopes of hydrogen, can make helium. Now that was all over pretty quickly. We've done the calculations. Some very clever people have come up with this number. We looked at the fact that about 75-25, I think it's roughly that amount, is produced from the hot dense period. We look out and that's exactly what we see. There isn't enough stars in the universe to produce that amount of helium. So therefore we know that that helium was produced in the Big Bang and has not been produced in stars. Hence, this, I think, one of the most telling periodic tables that you'll ever get here, in that the Big Bang produced hydrogen and helium. By the way, but it's not in A level. So therefore, you've got the Big Bang producing hydrogen and helium, roughly 75-25. And then, of course, after that, you need different things. So it says cosmic rays here, but you can produce these other things in stars. And then small stars, and then man-made, of course, the very, very large ones, which are down here. And small stars are basically like the sun, carbon, nitrogen, oxygen. It's a great diagram. Basically, you can see where a lot of elements need to be produced in supernovae, type 1a and type 2 supernova, of course, from this course as well. So you can see, but only hydrogen and helium produced in 75-25. Now, what I've done here is I've boiled that down to a good exam answer. Why is there this cosmic abundance of hydrogen and helium at 75-25? Tell me, Mr. Examiner, why? Well, I've got an answer for you. Because the universe expanded too quickly to form heavy elements. This is consistent with observations of the fusion of hydrogen into helium during the dense period. There you go. So in other words, there was a dense period, that's when the fusion taken place. The observations are consistent with that, and there just isn't enough stars to be able to produce that amount of helium that we see. There you go, that's our three pieces. 1, cosmic microwave background, that means we worked out that the universe was hot at one period. 2, the redshift of galaxies, that means that at some point the galaxies were nearer together because they're expanding away from each other. And number 3 is that when we count up all the hydrogen and helium in the universe, there's too much. And it must have been produced in a hot, dense period of the universe. A fusion activity took place between hydrogen and helium to be able to produce that amount of helium you see. Okay, the actual story is far more complicated than what I've done there, but that's why you should do a degree in physics and astrophysics and work out what these real answers are. That's why I did it. My A-level teacher just kept teasing me all the time, just like I'm teasing you. So go and do it. It's a great job. Okay, so this is what it is. Now, I've nobbled this from a non-AQA exam. It says, describe the main features of the Big Bang Theory and evidence that supports it. This is only 4 marks, but it'd likely be 6 marks because this one didn't have the cosmic abundance of hydrogen and helium. So do your basically 2 marks each. 2 marks for cosmic microwave background, 2 marks for redshift and the conjecture from that, and 2 marks again for the cosmic abundance of hydrogen and helium. I say cosmic because it's hydrogen and helium out there, not just in the sun, because the sun is just one little poxy star in the pretty old galaxy called the Milky Way. And there you go. So main features, got our expanding universe, explosion, in inverted commas, because it wasn't a chemical explosion, sorry chemists, and redshift of distant galaxies in keeping with Hubble law. So you mentioned Hubble's law there, the evidence, and of course you've got hydrogen and helium. You've got CMBR after got Big Bang redshifted. There you go. So it's been added to specifications, this one, since the question was made, and also doesn't feature in some of the OCR, I think, as well. So there you go. Right, last thing, quasars. I mentioned 3C273, which was the first of these. Astronomers looked at that and looked at the spectrum, and all the lines were all shifted off. And it's what's going on in that star? Why is it moving away from us? And then when they worked out how much it was moving away, and then when we tried to work out how far away it really wasn't moving as a cosmological difference. And if we zoomed into 3C273, we'd probably see something like this. A massive active galactic nuclei. I mentioned these before in a previous lesson. Active galactic nuclei, where there's a black hole eating stars and material. And then at the edge of there's massive X-ray, radio, everything output. Optical, producing a object that looks like a star, because these are stars here in the Milky Way, and this is at the very edge of the universe. Very, very large distance. In fact, 3C273 appeared to be not that far away. We've got much, much higher redshift and very large distance galaxies. Now, so fact 5, they're very powerful, the most powerful objects in the universe. They have an active galactic nuclei. That means there's a supermassive black hole which is accreting material into it and producing from a very small area. That small size, it's about solar system size. They're at large distances. They're discovered by very powerful radio sources. So these things here, these lobes, are very powerful radio sources. That's what we discovered, and therefore then we went to look and found the opticals were pretty unremarkable, really. You can see how that looks pretty much the same as that one, but that one is a supermassive black hole accreting material like whole clusters worth of stars at a single gulp. And then with modern telescopes, we've associated them with all manners of emissions. So that's your quasars. Quasars, very large distance, very exciting things. And here's some questions. Cygnus A, maybe the nearest quasar you've discovered, and there's the redshift. Remember redshift, delta lambda over lambda. Distance, calculate the distance to Cygnus A, state the appropriate unit. Here's the answer, 4 marks here. Great, here we go. So therefore you can try and get that distance from using Hubble's law. First of all, work out the recessional velocity using delta lambda over lambda and v over c. Of course, you know all those things. You've got the redshift of those. So get the recessional velocity from the redshift. And then, of course, get the distance to it from your Hubble law equation. So V equals hd. So remember, Z redshift is V over c. In this case, we don't have any wavelength information, so we've got to use the redshift equals V over c. Then you go to your Hubble law and do V equals hd. So get the V, put it in there, get your h, and you've got your d. In this case, you'll have your d coming out depending on what your Hubble constant you've used. If you've used Hubble constant, remember the Hubble constant is kilometers per second per megaparsec. So you have to have recessional velocity in kilometers per second to get the answer in megaparsecs. So be really careful about your units in this case. So get your recessional velocity, convert that to kilometers per second, and then that will give you an answer in megaparsecs. That's why they've given you this unit here, because some students will just go in blindly, stick in the numbers, and then stick any old number because they won't be thinking about what answers are going to be coming out. First quasars were discovered in 1950. What properties of quasars led to their discovery? Of course, just look at the fact file. High radio emitters. Okay, very dim. High redshift. So therefore you end up looking at those. So get those in your answers. There's the answers. Sorry, didn't warn you, did I? But there you go. So there's your recessional velocity in kilometers per second, and then of course the answer 263 megaparsecs. That's about right. If you're talking about hundreds of megaparsecs, you're talking in the right regions of quasars. Anything larger than that, and of course strong radio sources, 1 mark for that. And there we are. Here we are again. So do your practice on this one. I put some nuclear stuff in there as well. Put some gas stuff in there just for fun. But also this is what you've got to be able to do. Remember, CCD function only comparing to the eye. In this case, Rayleigh criterion, one of the backbones of evaluating telescopes. Background radiation here, it can be both ways actually. It can be a radioactive background radiation, or it could be cosmic microwave background radiation. Hubble law we just mentioned this time, and certainly its relation to working out how far quasars are. Pick all of these, you need to know them all. Go back and look at all of my lessons previously, and then you'll be fully tooled up. So good luck, everyone. I put some different ones on here because these are the ones which my students anyway said they weren't that clear on. So electron scattering, 3 types of decay. There's actually more types of decay of those. And so anyway, there you go. So ignore lens equation because that was a previous specification. And just to sum up, the last part of the specification that we're doing here is Hubble's law. We looked at the redshift, which gives this. Remember, redshift equals V over c. That's where you get the V from in here. And then D, of course, is in megaparsecs in this case, assuming you put kilometers per second in there, because the H is a non-SI constant. Inverse H, which gives you the age of the universe. Qualitative treatment of Big Bang. Quasars, and there we go. There's our fact file essentially about this. It has power output on here. Generally, that might come in. In different aspects. Not sure. I haven't seen any questions to do with power output of quasars. Basically, it's very large power output. I can imagine basically the intensity of the Earth is given in watts per meter squared, you're asked to calculate the distance to it and then using the inverse square law. So intensity, of course, is luminosity or power divided by 4 pi r squared. And that r squared is the distance to it. That's got to be in meters if you're going to do a intensity at Earth. So that's probably how you're going to get the power output of a particular quasar from there. So beware of your units here, because it might be given the distance in megaparsecs to a quasar. Convert it into meters if you're doing anything to do with the inverse square law. Okay, so be wary, everyone, of the units in there. Haven't seen one in an exam yet, but I'm sure there might be one. Somebody might correct me. There might be one somewhere buried in some exam that I haven't seen. And then, of course, formation of quasars from active supermassive black holes, which is just basically all the stuff's going in. Quasars, which are very bright objects, and supermassive black holes are formed by constantly accreting material. Okay, bye-bye.